Chapter 4 Solar Radiation and Earth, Section 4.2 Solar Output and the Earth. So, what I'm talking about in terms of solar output is the radiation that is emitted from the surface of the sun, and this energy is the primary energy that drives all kinds of other systems on our planet. This solar energy is responsible for weather and climate, ecosystems, the hydrological cycle, the weathering and erosion of rock surfaces. And this solar energy is created at the sun through nuclear fusion. Because of the sun's immense size, gravity is very, very strong, and it pulls hydrogen atoms towards the core of the sun. With enough gravity, two hydrogen atoms are fused into one helium atom, and this nuclear fusion creates high temperatures and radiation. At the core of the sun, scientists estimate that the temperature, because of fusion, is in the neighborhood of 15 million degrees Kelvin. This heat energy at the core then travels to the surface of the sun primarily by radiation. So radiation, what I'm talking about is, these atoms are transferring energy by photons from one atom to another atom. This process takes about 100,000 to 200,000 years to move the energy from the core to the surface of the sun. And that gives you an idea of how large the sun is. The last 20% of the journey, convection becomes a more important process in moving the heat energy towards the surface. At the surface of the sun, the temperature is about 5,800 Kelvin. And this radiative surface, the name of it is the photosphere. Now, with a temperature of 5,800 Kelvin, plug that number into the Stefan-Boltzmann equation, and the equation suggests that the amount of radiation emitted from the sun's surface should be in the neighborhood of 64 million watts per meter squared. Now, plug that number also into Wien's law, and Wien's law tells us that most of this radiation that is being emitted from the surface of the sun is going to be centered around 0.5 micrometers in the visible wavelength band, so closer to purple and blue in terms of individual colors within the spectrum of light. We have many satellites observing the sun. For the most part, the sun's output seems to be constant, but there are the sun does produce solar flares, and solar flares can be dangerous and cause disruptions on Earth. And I'll talk more about that in just a minute. So we know this radiation travels outward from the sun and diffuses as it moves in a spherical shell towards our planet. These are some of the major features of the sun. So the outer surface of the sun is called the photosphere. On this photosphere, we see dark spots that are called sunspots. The corona is the atmosphere of the sun, and it's much hotter than the sun's surface. And the cutaway shows us the core, where fusion is taking place. The distance from the center of the core to the sun's edge is 700,000 kilometers. The yellowy zone is the radiative zone. So here, energy is being transferred from atom to atom through radiation transfer. So photons leaving one atom, entering another one, creating heat, then produces another photon, and so on. And in that, the sort of beigey colored zone is the convective zone. So where convection becomes more important in moving the heat energy towards the sun's surface. The final feature that is shown is a solar flare, and these solar flares are shot out into space, composed of ionizing gas and other kinds of particles, and occasionally our planet intercepts these solar flares. So the energy emitted from the sun's surface travels in this spherical shell, and it becomes less intense as it travels through space, and we can model that process with the inverse square law. So 64 million watts at the sun's surface. By the time it reaches the Earth's outer atmosphere, the intensity of that radiation is 1,370 watts per meter squared. This value was once called the solar constant. It was believed that the sun didn't vary that much in terms of its output. There is evidence to suggest that the sun has, there have been times when the sun has produced less radiation, and that is the Little Ice Age, and we'll talk about that in an upcoming chapter. So in the truth is the sun's output is not constant. Sunspot activity is correlated to solar emission, and it's the opposite of what you think. The sunspots don't reduce the emission of radiation; they actually increase the radiation. So when there's a lot of sunspot activity, radiation or output is higher. When there are less sunspots, it's lower. And approximately 300-400 years ago, astronomers noticed that the sun had very, very few sunspots, and that seems to correlate with this Little Ice Age period, when temperatures were probably about, on a global average, about a degree less than they are today. Climate researchers have discovered that variations in global temperature may have been the result of the sun, and we're talking about time periods, centuries, not days. Solar flares can produce problems, and I'll talk about those in a minute. So we have a whole bunch of satellites monitoring the sun. One of the things that we're monitoring is solar output. So here we see the measurement of solar output between 1978 and 1999, and measured by a number of satellites seen in the top half of that graph. Some satellite instrument called HF, Ackermann 1, ERBS. So these are all put together into a single composite, because each satellite needs to be calibrated. They're all calibrated slightly different, so you can see the values vary from 1364 watts per meter squared to 1374, and the value probably is more in around 1367, 1366. You can imagine it's very hard to calibrate a satellite instrument in space, and you can see there is this cycle. So the amount of radiation, the variance of radiation seems to be about 1 watt. Now that's not enough to cause a significant change in the climate of the planet. We would need something more in the order of about 10 to 20 watts of variation. Now, if you measure the distance from one peak to another, it's about 11 years. So that these sun cycles last for about 11 years in length. There are other cycles too. There's a 22-year cycle, an 80-year cycle, but they're not that important for this part of the course. So here we can see these cycles. Now this is actual sunspot numbers. So from peak to peak, it's about 11 years. The black line is a moving average. So we can see that sunspot activity did get higher when we moved in from the 1900 to 1950 to 2000. It's now on a downswing. So temperatures are still increasing globally, and actual solar output is declining a tad. So you can see sunspot numbers were very, very low between 1650 and looks like about 1725. This period of low sunspot activity is known as the modern minimum. Okay, let's watch a solar flare in action on this video. So as I said, we have a whole bunch of satellites measuring or monitoring the sun, and here we see a solar flare coming from the surface of the sun. So these are huge. Earth would be very, very small compared to these. So these solar flares can hit the Earth, travel through space. They disrupt radio signals. Satellite transmissions can cause power surges. There's a fear that there might be one that's strong enough to affect some of our electronics that depend on computer chips. That these computer chips may actually be short-circuited. So they'll get a power surge and they'll burn out. Now, can you imagine the sort of disaster that could occur to human society if we lost a sizable portion of our computer chips?